Today, I wanted to talk about my PhD trajectory and specifically about controlling behavioral diversity in multi-agent reinforcement learning. So the process we're going to go today is the same as what I was doing in my PhD. So first, I'm going to motivate a bit why we need to think about diversity and collective intelligence. Then what is the current state of diversity in learning? And then the three contributions we made, which is how we can enable this diversity. Once we have enabled it, how do we measure it? And then using this measure, can we control it in a closed loop fashion? So first of all, a little bit of motivation. So this is quite a cool video, thanks to nature. And here we can see some ants that are tackling a shared task, which is to forage, and to do so, they have to cross this bridge. And these ants are basically physically identical, and they have a shared objective. But to achieve the shared objective, they have to assume different roles. Some of them will be farming a bridge, while the others will be go for foraging. And the ones that are farming a bridge, they're not directly incentivized to do so, but in the long term, this is beneficial for the collective. And this is something we call collective intelligence, which is not just the sum or the maximum intelligence of individuals, but it's something more, something emergent. And this kind of intelligence is commonplace in natural systems. And what we try to achieve and investigate is how we can achieve this intelligence in robotic systems. And in particular, as a mean toward collective intelligence, we look at diversity. So we don't want to achieve diversity per se, but we want to achieve diversity as an enabler of collective intelligence. And we have seen that in natural system, diversity is commonplace, ubiquitous, and it's key to success and to resilience. While in robotic systems, diversity is underexplored. In particular, it's considered an inefficiency because now you have n different individuals. So the goal of today and the goal of my PhD was to shine a little bit of light into how we can enable diversity in robotic systems towards collective intelligence. So now that we have seen a little bit, maybe the motivation, what is the current state of diversity? Why do I even have to do this at all? So I'm just going to begin by recap a bit the learning paradigm we use, which is reinforcement learning. If you're familiar with reinforcement learning, just look at the golden retriever. It's nice. So in reinforcement learning, there is an agent and an environment. The agent receives an observation, which is Matteo is asking me to sit down. And given this observation, it takes an action. OK, I sit down. And then the environment basically gives a reward signal, which is, OK, you get a treat because this action was good. And so the agent goes through this decision-making process, getting rewards and action, and the rewards reinforce positive actions. And the negative rewards penalize not negative actions. And looking a little bit into more of the formalization of these, we can think of the agent as having a policy that takes as input the state of the world and outputs an action, which is then fed to the environment again, which outputs a new state and a new reward, and the agent can learn through this interaction loop. In the context of multi-agent, not much changes. There are just multiple agents now that are concurrently interacting with the environment. Each of them has a policy, which takes a local observation and outputs agent action. And also here, the differences are that the rewards now are a vector, one for each agent. They could be shared, but we consider one for each agent. And the observation is just a function of the state. You can imagine the agents having a camera or something that takes just a partial picture of the whole state. So the core component here is the policies. So these pies is the strategies of our agents. And what is done is the literature is that people use parameter sharing. So the parameters that parameterize these policies are shared among the agents. So they're training a collective brain, basically, which is then deployed to each of the agents, but it's identical. And what this implies is that if you have a shared policy, when you receive the same input, you will have the same output. So if I have a blue square, then my action will be going up. So how the agents are able to use this policy to cooperate is that, well, if they just see two different observations, then of course they can take two different actions. So in reality, they can use different observation to basically cooperate. But the problem is that what if I want diversity? And diversity is when we have the same observation, we should take different actions, right? So how can we do this if we have parameter sharing? Well, what they do in the literature is that you can have this index that you prepend to your observation. that you can use to condition on. So the agent can say, okay, I'm agent I and observe the blue square. Well, now I can take the action up. While on the other hand, I see J, then I take another action. So you have this kind of discrete indicator that says who you are as part of the observation to be able to take different actions. And this indicator could also be something continuous. Okay, maybe I decide my role based on my position in this lecture hall. When I'm here, I'm more of a lecturer. When I walk towards here, I'm more of a student, and it's a continuous distribution with your roles. So this XY could be my distance to the computer determining my role. And this is similar to pre-prompting in LLM cases, where you can say to an LLM with shared parameters, you can say, oh, you are a reviewer, oh, you are a code designer, and you can give different roles by context. So we call this context behavioral typing. And basically, what we know is that what we see is that basically you can, homogeneous agents are able to infer roles based on this context. And we divide this behavioral typing into explicit and inferred. Explicit would be when you have an explicit index, and inferred is like more inferred from the context. But the problem here, there are multiple problems. First, now you're relying on your context to infer the role. And the problem is that when your context is noisy, when your input is noisy, your roles will be noisy. So essentially, you're brittle. And also, diversity is not quantifiable and controllable easily because you have this big shared policy. So you're essentially fitting multiple behaviors into one strategy. And what is the catch of this? So you will have an agent which is a doctor, it's an engineer, and it's a lawyer. And this is the trend nowadays with LLMs. You have a monolithic model which contains all the skills that you need, and you can, given context, use some of these skills. But we humans don't do this, right? We specialize into special field, and experts, there are different human experts. And it could be a question of capacity, like how many behaviors you can fit into one single model, or so on. So this is an open debate. But essentially, if you have this very big model, then you will have a situation like this where you're discussing diversity and everyone is actually the same. So how do we enable diversity beyond parameter sharing? And before talking about this, I just wanted to give an overview. We have developed alongside this research some tools to simulate and train multi-agent systems. And in particular, the ones that you will see all the tasks from today, it's VMAS, which is a repository of multi-robot scenarios. Now we have more than 30 that have different tasks. Some are bio-inspired, some are robotics oriented, some are games like football, and everything you will see today comes from this simulator. So before even tackling the problem of enabling diversity, we have to understand what does it mean for a system to be diverse. And we identify two main classes of diversity, one on the behavioral side and one on the physical side. Physical side is when the agents differ based on their hardware, based on their capabilities, something physical, while the behavioral side is about their software, about their behaviors, and about their strategies. And the behavioral side further subdivides into two categories. So when you have different behaviors and you have a shared objective, or where you have different behaviors and you have different objectives. And this kind of intersection of this Venn diagram gives us four mutually exclusive classes, you see in the bottom, that are really nice to categorize existing work. For example, in the green area, you have physical agents which are also behavioral different, but are optimizing for the same objective. So for example, here you can see agents that have different speeds because they have different capabilities at the physical levels, but they're optimizing the shared objective of covering an underlying mixture of Gaussians, and they do so via different behaviors. And in the cyan area, you might have soccer, for example, where you have identical agents that have the same objective, which is to score a goal, but they might have different behaviors, like an attacker and a defender. So how do we enable diversity? It's pretty simple. For now, we just disable parameter sharing. So we allow every agent to have different parameters. And in this slide, the only thing that probably we should focus on is that the model with all blue is parameter shared, and the model with the different colors means that each agent will have different parameters. This model also allows to communicate via GNN network, but it's not really the focus today. So just think that we now have a model that has parameters that are individual to the agents. And what I'm interested in here is to compare, just to see what is the difference between having parameter shared and not parameter shared models. So this is a task where two agents need to swap places in a narrow corridor, and they need to go to the respective goal. And so for this, they need to give way to each other. And so one of the agents will need to give way to the other. So we train this in simulation in the top. And we deployed zero shot in the real world in the bottom. And as you can see, heterogeneous agents are able to do this no problem. The agents here are only observing and communicating the relative position to each other. So they don't have observation about the goal. So now let's see what the homogeneous does. In simulation, the homogeneous is actually able to do this. And the way it does this is because it can condition on the relative positions to infer who should give way. So I can say, oh, I'm here, you're here. So okay, let's now coordinate. I can pass you, and we do it this way. But when it goes to the real world, something very interesting happens. So you can see that the agents first are able to make the swap. But then, since the real world is intrinsically noisy, and they're using the relative positions to infer the role, they get confused and they swap roles again. And since the roles are dependent on the relative positions, and the relative positions are noisy, now the role is noisy. And so they will keep swapping back and forth until they finally figure it out, and they are able to complete one swap. Okay, so hopefully this was a little bit of motivation why parameter share has to be considered carefully. But now we have these different agents. So what about measuring the resulting diversity? So this is the current state of affairs. On the top, you can see homogeneous parameter share policies, all black, and then heterogeneous policies with different parameters. We use different colors to encode these. So what are these policies? So when you have heterogeneous agents, basically, given the same observation, they will output different action distributions that we can see here, for example. And so the goal of measuring diversity is really the goal of comparing these different action distributions. So how do we do that? And what we came up with is the metric called system neural diversity, which is designed as follows. So first, you define a distance between agents' outputs. And since the agent outputs we saw are action distributions, this could be a statistical distance. Then you average this distance over agent pairs. And then you average it for each observation in a set of evaluation observations. So in reality, this is just computing this metric in two layers. At the bottom layer, you're taking pairs of agents and comparing them. And so you build like behavioral distances among pairs, and you can structure this in a matrix. And then at the higher level, you can aggregate the elements of this matrix into a global readout. And this is a scalar value that tells you how heterogeneous is your system. And so a little bit more about the distance that's used to compare pairs of agents. We use Wasserstein metric because, well, first of all, it's a matrix, so it has properties like triangular inequality that Keil divergence doesn't have. But furthermore, with respect to Keil divergence, it has this nice property that if you're trying to compare two Gaussians, and these Gaussians their standard deviation tends to go to 0, and so they become deltas. Well, as they become deltas, the KL will go to infinity, but the Wasserstein distance will go to the distance between the means of these two Gaussians. So in reinforcement learning, the distributions tend to go to deltas because as the agents explore, they get more and more certain. And so we don't want the diversity to increase as they get more and more centered. I mean, we want it by degree, but not to diverge. So this is the reason why Wasserstein is used here. And so just to recap how this measuring metric works is that you need an observation set, which is a set where you're going to evaluate your agents on. If you collect these, you have to be careful about how you collect this set because it has to be representative of the observation space. If you sample the observation space uniformly, then you might evaluate the agents in observation that they're not trained on. But what we do is that we collect it via rollouts. So those are observations that the agents are likely to see because they have seen them. And then building this set using rollouts, then we can take observation from this set. For each observation, we feed it to all the policies. And then we get the policies outputs, which are the action distributions. Over pairs of policy outputs, we measure the Wasserstein distance. And then we aggregate these distances again back into a system level value. So all of this is quite a detail. The important thing to remember about this metric is that given a team, I can have a readout, which is a scalar, which tells me how behavioral diverse they are. And it ranges from 0 to infinity. One cool property about this that we're going to use later is that There are multiple reasons why it was designed this way, but this is one. What we want is that the diversity should not be dependent on the number of agents as long as they're behaviorally equidistant. So let me explain this. In the case where I have two agents at distance x from each other in behavioral space, then the SND will be x. Now, let's say I add a third agent, which is also a distance x from the two existing ones. I don't want the metric to increase because I think that all the agents are still at distance x. So that's the same dispersion, independently whether then there are 2 or 3 agents. Other metrics, for example, here you see HSC, which is another from the state of the art, take a different use, which is totally fine, which is, okay, I have more agents, so I have more diversity. But for us, it's important that diversity is not really dependent on the number of agents, because when we will employ this metric for control, we want to be able to control teams independently of their size. Another property, which I'm not going to discuss today, but the overview of this is that we want to measure behavioral redundancy. So as more agents have the same exact behaviors, we wanted the metric to decrease, and other metrics did not do this, but this is not important for our goal. Okay, cool. Okay, the goal of the talk, now we finally arrived to the important bit, controlling diversity. So what is the current state of affairs again? The starting state of affairs is that we have these agents, which are different parameters, and now we have a metric to measure how different they are. So why do we want to control diversity? Well, let's first see what people do regarding with regards to diversity. People have understood that diversity leads to better exploration and to better performance in some situations, some tasks. So what they do is that they develop solutions to promote diversity. And the typical way they do this is via an additional term, either in the reward function or in the loss, which basically incentivizes diversity and pushes agents to be different. And you can see here the intrinsic reward is like you have the reward of your task, and then you add an intrinsic reward for diversity, and the loss is similar. And what are the problems with this? Well, I guess this is not really controlling diversity. It's more like promoting diversity. And furthermore, like you don't have a real readout on diversity. You might have a proxy through the value of this loss, but it's not really a measure. But the most important of all, I think, is that you are modifying the task objective. So the interaction between the loss for your task and the loss for promoting diversity, it's non-trivial. And depending on this alpha, the loss of diversity could compromise the optimality of your policies because you're effectively polluting the objective. So the idea is, can we ground diversity according to our measure and then use this measure to perform closed loop control in like a control theory way? And can we do this without changing the objective at all? We want to keep only the original reward and the original loss function. Why? Well, because this way we would be able to formalize a hard constraint. So I want to learn the task such that I satisfy the diversity constraint. And I never violate it, or there is no slack in the violation of the constraint. It's a hard one. And also, if you think about it, the search space of policies when you have heterogeneous policy, it's really big. And so by applying a diversity constraint, you can cut this space at a specific diversity level. And you say, OK, I only want to look at policies that have diversity X. So now everything that doesn't have this satisfy this criteria will be outside of your search space. So you have a much smaller search space. And homogeneous is a specific case because you can say, OK, I want policy with diversity 0. And you can cut at that level and you get homogeneous policies. And yeah, this does not pollute the core objective. So here you have to take a leap with me because I'm going to explain this through an analogy. And it's full of Italian stereotypes. I can do this because I'm Italian. So Mario Rossi is a typical Italian. He eats pasta and pizza every day. He speaks with his hands. He drives crazy and mostly on Vespas. And he's very attached to his mother. But most importantly, he will always take the average decision, the typical decision in any situation. So when Mario Rossi goes into a pizzeria, what does he order? Of course, a margarita, because that's the most typical choice. But if someone else is at his table and maybe Johnny and it has different taste, they will order something more exotic, maybe pizza with pineapple. And maybe I'm also at that table And I think of myself as quite sophisticated Italian, so I'm like, what about the pizza with burrata instead of normal margherita? So this is totally fine. We are all at the pizzeria and we are observing the menu and we're taking different choices. But now we can structure this and think about it in a different way. So what if Mario orders a margherita? And then I can define my choice with respect, okay, I take what Mario takes, I just want burrata on top. And then Johnny can define his choice as like, okay, I take what Mario takes plus pineapple. So it doesn't really matter if Mario exists. Mario could be there with us and I'm like, okay, Mario, what do you take? Okay, I take what you take plus this. Or it could be like, I go in the restaurant, like everyone knows Mario and everyone is like, okay, so I take what Mario takes plus a burrata. And it doesn't matter if Mario is there because everyone knows what Mario would take. It's a shared reference. And also it doesn't matter who is the reference. I guess Johnny could be the reference, but then everyone would have to know, have a common knowledge of Johnny's decisions. Yeah. So going back to this, does Mario Rossi exist? In reality, it does not matter because as long as everyone knows what he would do, it doesn't need to physically exist. And in fact, in our case, it does have a policy, it does exist, but it's just a virtual agent that acts as a reference. So let me go back to the domain of reinforcement learning. Of course, the pi will be the pi. And the way we do this is the following. So the first trick is about reformulating the policies of the agents as a shared component, a homogeneous policy, plus a heterogeneous deviation from this component. Then if you do it this way, you can see it in action space that you have this shared homogeneous policy, and then you have all these deviations from all of the agents branching off. And this homogeneous policy is trained in the same way that we've seen in the beginning with parameter sharing. And so in our case, we like that there exists this homogeneous policy because we can use parameter sharing and have some knowledge in there. You could also have a version of this where pi h does not exist and you just take the center of mass of the heterogeneous agents, but that you wouldn't have the benefits of parameter sharing. And so what you can do with this is that you can now take the diversity of the policies defined this way. And once you have the diversity of the policies defined this way, well, you have everything because you have the desired diversity, which is, let's say, my input, what I want my metric to be. And then I have the current diversity in my system, which is their current distribution. And I can compute a scaling factor. And by multiplying the heterogeneous component by the scaling factor, I can rescale these policies in behavioral space to be closer or farther away from the homogeneous reference. And so if I have a desired diversity of 0, as indeed as is the desired diversity, then this term will be 0 and all the policies will collapse onto the homogeneous one. So everyone will be homogeneous. But as I increase the diversity, the desired diversity, this policy will expand in behavioral space. And the deviations are what is learning the direction of this expansion, but the absolute scale is what is determined by the scaling factor. And the scaling factor, it's only computed during training, and during execution is fixed. So you can deploy this in a decentralized way without any centralized infrastructure. Yeah, overall recap of all this. And the steps are the following. Redefinition of the policies as the sum of heterogeneous components and homogeneous components. Measure the current diversity of that. And then you have the desired diversity. With these two values, you can compute the scaling factor, desired divided by current. And then you can multiply the heterogeneous deviation by the scaling factor to obtain the rescaled policy. And what we achieve with this is that after this rescaling process, the policies are guaranteed to have the desired diversity. So you will, we prove it in the paper, and you will guarantee that you will achieve what you requested in terms of diversity. Cool. So an example of how this works in practice, because it's a bit abstract as of now. So in this task, we're very simple. We have two agents that need to go to their goal, the blue and the orange. Each agent is observing both goals. So they need to be heterogeneous because one agent needs to focus on the first observation and the other agent needs to focus on the second observation because they need to go to two different goals. So what we plot here underneath the goals and the agents is the distribution of diversity over observation. So for each observation in this task, we say, okay, how heterogeneous is the team if they were to be in this observation? So yellow areas are areas where the agents would take a very different decision, and blue areas are areas where the agents would take the same decision. And we first train an unconstrained model. Unconstrained, we mean heterogeneous, but without any constraint. You can be as heterogeneous as you want or as homogeneous as you want. And you can see that there's something interesting, like something that we want to see is that between the goals, there is diversity, because between the goals is where you want to be maximally different. You have to go in two different directions. So then we apply different level of control diversity to this task, and we plot reward and diversity. And just focusing on the bottom rendering and the one on the left, here is where we force them to be homogeneous. And when they're homogeneous, basically, there is no diversity. So all the landscape is blue because they will always take the same decision. And the best they can do with this is to go to the middle point between the two goals, which is the center of mass between the two goals. Like, they cannot distinguish who is who, they cannot behave heterogeneously. So let's just take the average. But you can see, as I increase the diversity budget, the diversity constraint, then more and more diversity is placed in the important place. And here the important place is between the goals. Because again, this is where you want to be maximally different. And another place where it's important that we can look at to understand if this is working is that in the line that is connecting the goals, but when you're not in between the goals, then you want to see zero diversity, because if you're heading in the direction of both goals, it doesn't matter what agents you are, you will always take the same action. You will go towards the goals. So as you can see here, these areas have very low diversity, forming this kind of cross shape. And the landscape of the diversity also looks quite regular compared to this one, which is the unconstrained one. So maybe there is also some benefit in this. But in the right plot on the top, you see the diversity. So the different lines are different control inputs, and the outputs are different measures. So you can see that when we control a diversity level, we always obtain exactly that level very precisely. So this confirms that the control works. And then on the left side, you see that the reward, that as you increase the diversity request, in this case, the reward increases because the task needs heterogeneity, needs diversity, so it's beneficial. And then the blue line is just an unconstrained model, which is a little bit less stable, but in this case, it's fine. It's the best as well. This was just a case study for understanding how the algorithm works. Cool. And if this makes sense, some results. So the first task we look at is dispersion. And in this task, basically, 4 agents are spawned in the middle. And they observe the same number of food particles as they are, so in this case 4. And they are rewarded for consuming food. And to consume food, when at least one agent consumes a food particle, the whole team is rewarded. So the optimal policy here is that each agent should only consume one food, because sending 2 agents to the same food particle, it's redundant. So we train on this task homogeneous agents, unconstrained heterogeneous agents, and agents with control diversity. So when it comes to homogeneous agents, this is very interesting. They are forced to do the same thing. So starting in the same position, they need to go to each goal one at a time, all together. And you see here that they have a little bit of difference, but that's just the stochasticity of their policy. In the unconstrained case, the agents can take different decisions. So they can go to different goals, but they're not finding out the best policy. Like, they're still sending 2 agents to the same food particle, which is suboptimal because you could send agents to different particles. And in the last case with control diversity, we boost the diversity to a high level and we say, okay, you need to be at this high level. And well, the agents immediately figure out that the only thing that they can do with such a diversity burden is that they need to take maximally different choices and hence go to the different goals. And they will learn very fast to each tackle a different food particle. In a similar scenario, in this case, the agents need to cover a uniform distribution. They start in the same position, and the team is rewarded for the total area that's covered. So in this case, again, for homogeneous agents, unfortunately, they start in the same position, so they will have to choose similar things. They will deviate a bit thanks to their stochasticity, but still they will mostly sample the same area. For the heterogeneous agents, now they are able to take different choices in different trajectories, but eventually they end up resampling some already covered areas. But for the heterogeneous agents with the constraint, then if you force them to be quite different, you can see that even in the beginning, they branch off in the most heterogeneous way, and then they also kind of section the space to sample in the best way. So again, achieving the best reward. And in this case, basically, we show that the constraint allows to explore better. And the last task is more of a high-level, long-term decision-making, because here you have a team of 2 red agents chasing a green agent. And these agents are collectively rewarded for tagging the green agent, and the green agent is negatively rewarded for being tagged. They still receive a shared reward. So we try to train on these homogeneous agents, and we see that despite being learning very good policy, they need to take the same action given the same observation. So they will just blindly both chase after the green agent, taking the same kind of trajectory. It's a bit useless because you only need one agent to do this, right? And in the unconstrained heterogeneous case, similar things happen. So both agents, again, kind of chase blindly after the green one. So what happens if we boost a little bit and try to control the diversity to a higher degree? Well, something very interesting. We lead to the emergence of very new strategies that are at higher diversity levels, and that wouldn't have been discovered automatically without this constraint. For example, the first one is ambushing, where the agents split up to cover more area, intercept the agents. So here you can see one of the red agents navigating across an obstacles, and another like making a kind of ambush behind the other obstacles. Other behaviors are this one, which we saw emerge in multiple instances, which is cornering. So the agents perform a pinch maneuver where one of the agents first pins the green agent to the corner, and then the other closes in, basically trapping escape routes. Yeah. And lastly, quite an interesting one. This one is a bit more subtle. It's man-to-man marking. So similar to like football and soccer, one of the agents is interested in chasing the green agent, while the other basically keeps at a distance, trying to block escape routes. And the green agent basically will see that this agent is in that direction. So it will kind of use this position to condition the behavior of the green agent without actually going after and chasing it. And yeah, like none of these behaviors were incentivized, and the red agents are also rewarded with the same structure. They have the same physicality. But in this case, we saw that it's beneficial that the strategies, to have diverse strategies even when doing so. And you wouldn't discover this just by running unconstrained heterogeneous training. Okay, so for the last 2 slides. What is the limitation of this? So we introduce this as a method. It's a new perspective of looking at diversity and gives you this opportunity to have this control input. But the biggest problem is, how do I choose this control input? And there are multiple ways to do this. It's still an open question, I would say. You can compute the maximum task diversity given a task, and this will give you a range from 0 to that value. You can automatically tune it based on a outside matrix. So you could have an outside loop to optimize this control value automatically based on a proxy, let's say resilience or something like that. And another very interesting direction that we have taken is inequality diversity control. So up until now, we saw diversity as being the constraint is like, okay, I want a diversity which is a function of my desired diversity. And what we've seen so far is the equality. So I want my diversity to be exactly what I request. But the method that we propose is also able to do inequality constraints. So you could do something like, I want my diversity to be at least this value, or I want my diversity to be within a range. So if you don't have a clear idea of what value you're looking for, and you want to use something like this, you can do so. And in particular, you can boost in the earliest stages of training, you can boost exploration by setting a very high diversity lower bound, and then lowering this lower bound throughout training to allow for more homogeneity and sharing after the agents have explored a bit. Yeah, and lastly, this is something that after we have developed this method, we went like, okay, we think this is very useful. How can we empirically show this on a really high scale? And this is a project we've been working on for quite a long time now. It's not out yet. So I'm just going to show this video and not say anything about it. Thank you very much.